Okay, folks, let's talk about the Intel compiler. Again, the most important slide of everything, our legal friends. We will do an examination tomorrow at lunch about that. I brought probably 3 marketing slides. I couldn't avoid that, just to introduce you to the software environment. We have essentially 2 different versions of development tools for our processors. The first one is called Parallel Studio. That's kind of the intra-node development toolkit. And then we have the Cluster Studio XE. That's for distributed development, so cluster development. That's MPI and MPI tuning utilities. And so the Intel Composer is essentially part of a 4-stage cycle. At least that's what we promote as in our tool chain. So the Intel Composer basically is the main thing to create the program. That's the compiler, the libraries, and everything. Then we have something called Inspector XE. That's the correctness tool, kind of a debugger, to analyze parallel programs for correctness. Then we have the Amplifier XE. That's the part to do the performance analysis. We will cover that tomorrow morning. And we have a tool called Parallel Advisor. Well, that's, probably not so much of an HPC tool because most HPC people know how to think parallel. But it's basically a tool to give you some advice where you can find parallel spots in your code if it's still sequential, right? So, and you apply this cycle until you're satisfied with whatever level of performance you got or until you finished your software development. And as I said, the Intel Cluster Studio XE basically adds Intel MPI and the trace analyzer and collector to actually analyze MPI low-level communication. Okay, and why do we call it Composer? It was called Intel Compiler almost 20 years, basically. But nowadays, it's more or less a whole software chain of libraries, of the compiler, of different programming models. And so the marketing people decided to call it Composer to give it, some more touchy words and to express that. Basically, what we have in there is the inter-threading building blocks as a thread library. We have math kernel libraries. We have the Intel performance primitives, which is also kind of a high-performance library for image processing and decoding. We have the media SDK. So we have a lot of libraries around this Intel Composer to help programmers implement their codes. OK, that was the marketing part. Compiler generics. So most people are interested in what the compiler actually eats as a source code. So basically, we support almost the new standards. So we have full C++ 11 compatibility. We have C99 compatibility. And Fortran-wise, we support anything up to Fortran 2003 with minor exceptions, I would say. And we already support a good share of features of Fortran 2008. We are still working on it. And it's kind of embarrassing that 10 years after Fortran 2003 has been released, there is only 2 compilers out there, I believe, that fully support it. Cray is one of the compilers, and IBM, I think. We are lacking 2 features, so we're working on it. Let's put it this way. So what do we actually support? So as I said, almost anything out of 2003. The only thing that is missing is user-defined derived type I/O, so basically writing structured type to disk or to files, and Fortran templates. Basically, it's called parameterized derived types, so where you can actually do something like C++ templates in Fortran. And Fortran 2008, we have co-arrays in there, 2 concurrent loops, contiguous, all the I/O enhancements, and some other features are in there as well. So it's basically a good share of things that you find in real life are supported by our compiler, although we are not fully compatible yet. We are working on that, as I said. OK, what about compatibility to other compilers? So C, C++, it really looks good because we are fully compatible to GCC. That means we are not shipping our own runtime library. We are not shipping our own assembler. Basically, what we do is we compile everything to assembly level and then use whatever infrastructure we have on the system. So the usual Linux bin utils, as well as the runtime library of C. Fortran, unfortunately, we are completely incompatible to G-Fortran. So for Fortran codes, you need to decide either compile everything with our compiler or compile everything with G-Fortran. In the C world, you can at least decide to, compile some stuff with GCC, some other stuff with other compilers, and then mix and match everything together in a single executable. Okay, that basically I already said. And we also, feature-wise, we're also kind of compatible. So the main compiler switches are similar to GCC. And I think the only thing that we don't support from GCC is this nested function thing that they added to do something around the Linux kernel or something. That's the only thing we don't support. But other than that, we're also trying to emulate bugs of GCC to make us compatible as much as possible. Okay, this is not going to be a presentation about compiler switches. So this is just for your reference, like a cheat sheet. I'm not going through all of those. The default setting, obviously, is that our compiler optimizes for speed. This is also different to, for example, GCC, which just translates with debugging here. We have a more aggressive level, O3. That's also, typical. For your workload, you need to decide which one is the best to use. Usually, O2 gives the most correct result. With O3, the compiler starts to do nasty things about your code, and you never know if the compiler is broken or your code is broken, right? And so you really need to decide which one is the best. And sometimes also O2 gives a better result than O3, right? So this is kind of try and error and do performance analysis and see what is actually the best compiler switch. Well, there are, let's put it this way, there are always holes in specifications, like where the Fortran or C specification says undefined behavior, or this is unspecified, right? And with O2, this still works, and with O3, it starts to break because the compiler assumes something which is totally correct from the language perspective, but is not recognized by the user as a potential hole in the specification. And sometimes, well, the compiler is just buggy and triggers a faulty optimization or whatever. So there are always that kind of problems where the code is rearranged in a way that actually breaks semantics. Okay, then we have -G, that's the debugging flag. You will need that tomorrow for performance analysis. So basically what the compiler does is adding additional information to relate the assembly code back to the original source code. We have interprocedural optimization, profile-guided optimization. I will go over, just a second. I will go over those two. And we also have -Fast, that's our benchmarking switch. Because something like the typical benchmark suites require a maximum of 7 compiler switches. And so almost any compiler on this planet has a -Fast switch, which combines a whole plethora of compiler switches into a single one to fit this benchmarking requirement. Yes? -G? Usually not. No, it shouldn't, well, except that the binary loads a little bit slower. But usually, well, if you specify -G, it turns off optimizations. So you always need to have O3-G at the same time to enable optimizations and debugging, but then it shouldn't harm performance. It just adds information to the binary for the debugger or performance tools. Okay, then we have -OpenMP. That's our OpenMP 3.1 support. And we have -Perl and -Vec to turn on parallelization or auto-vectorization. Okay, so we also have a couple of architecture-specific switches where you can tell the compiler to generate code for a particular platform like Sandy Bridge or Westmere-based processors. You can either use, depending on where you are actually, if the login node or the build node is the same as the compute node, you can do -X host to tell the compiler, look at the platform and optimize for that processor that you find there. Or you can select any of these to specify which platform to generate code for. And the default is rather old SSE2 because that's kind of supported by AMD, by old Intel processors and Atom. Or you can select shiny new AVX code or code for the Xeon Phi coprocessor by the corresponding compiler switch. Okay, what's IPO? So IPO stands for Interprocedural Optimization, and the usual problem that the compiler has is that for good optimization, it needs to see all the code, right? But the programmer has a tendency to break the code up into modules, source files, libraries, and that kind of stuff. And usually when you do that, the compiler looks at one source file, compiles that, optimizes it, writes the assembly code to disk. Right, and this is done a couple of times until all the source code files have been processed. And with IPO, basically what we do is we take all the source code, put it into a single database, and then at the end of the compilation process, we look at the source code, we see all the source code, probably also including libraries, and then optimize the whole set of source code statements. We have two flavors of it, IP and IPO. IP is intra-file optimization, interprocedural optimization. So we analyze all the function inside one single source file, and with IPO, we basically take all the source files, basically at link time. So this is what happens. So in the first pass, the compiler basically reads the source code, processes it in a certain way, creates some intermediate representation of what the source code is about, writes that to disk, and then at link stage we have a second pass where we read all those mock object files and then produce the final executable. So we basically shift the optimization step from the compiler to the linker, right? So the linker does a little bit more. And you will see that this pass is really fast compared to the traditional optimization approach, and this takes a hell of time. I usually, well, for a big program, you can easily spend 24 hours waiting for the second pass. In this case, it really takes long. There are some algorithms in a compiler that are not linearly depending on the input size, like the length of the source code program, but quadratically or even worse. And if you add 10 times the stuff to the optimization path, you can easily imagine how much time that adds to the compilation process. But it can give you, depending on how many times you run the program, you can actually save some good share of time on the system, spending 24 hours waiting for the linker to come back. So, it's a trade-off. Okay, then we have profile-guided optimization. So the basic idea here is, let me show you this picture first. So there are some passes through the executable usually that are taken more frequently than others, right? But the compiler doesn't know that. So typically, a compiler optimization, if there is a if pointer is not null, then do something. The compiler would heuristically assume that this is just a safety check done by the programmer, and assume that the if branch is always taken, or most of the time taken, and it's just a safety check. But if there's something like I smaller than 10, and I comes from outside, the compiler doesn't know anything about it and does, suboptimal code. And with profile-guided optimizations, you can actually record the execution paths through the executable in a database and use that as a template for compilation so that the compiler knows how long are the loops running, how much function calls are there, what's the probability of an if-else branch, and that kind of stuff, right? And so what we do is, again, a multi-step process. The first step is we generate a profiling version of the executable. We run that version of the executable, hopefully with real-world data that actually, paint a picture of what you actually do at runtime. And then we feed this profile into the compiler again to tell it what is the behavior of the application at runtime. Okay, and hopefully we get better code out of that. Okay, reporting. Reporting is especially useful, and GCC really lacks good reporting features. So whenever you want to find out what GCC did to your code, the only thing is read assembly code and figure it out yourself. And so a good compiler is able to tell you anything about what it did to the source code. And this is where this optimization report comes into play. So you can tell the compiler, please tell me what you did. Right? And you can, first of all, you can turn it on. You can dump it into a file. And most importantly, you can also restrict the information. So I'm working a lot with OpenFOAM. And when I tell the compiler, please turn on opt report, I get 0.5 GB of log files with reports. Okay, this is not very useful. But what is useful is if you know that your application spends so much runtime in a certain module, you can restrict the optimization report to that particular function, hotspot, module, whatever, or source file. Right? So this is a feature that you need to selectively turn on for a couple of source files to get a closer look into what the compiler does to that. Not all of them, right? You had a question.
I find these optimization reports, even when you zoom in on the inputs, they're very difficult to understand.
Right.
Like, I mean, if you use the Cray compiler, for example, you get source code back, transfer and take it, what line. Is there a way to get like annotated source code out of the?
For Fortran, there is. Yeah, but not for C, I think. Okay. And of course, you can also restrict the optimization report to special phases that you're interested in, like the interprocedural optimization, intermediate level optimization, high-level parallelizing optimizations, high-level loop optimizer, and that kind of stuff. Right? So you can really select what type of stuff you're interested in. So if you want to, for example, know if your sub-optimally coded matrix multiplication is rearranged in a way that it's better for the architecture, you can look at, for example, where is it? HLO distribution, where we actually switch around the loops, right? Or we also have a re-rolling phase where some programmers unroll a loop, and the compiler, the first thing it does is roll it back to stride 1 and do it again in a different way, that kind of stuff. And what you essentially should get out of it, Ben, that's probably the answer to your stuff. The whole optimization report is a pain, right? But if you restrict it to, let's say, the high-level loop optimizer, you get something out that looks like that. So we have a loop nest at 7, 8, 9. That's the source lines. We have a permutation, 1, 2, 3, and the outcome is 2, 3, 1. So that essentially means what was the outermost loop is now the innermost loop. It's like a mathematical permutation. And that's more readable than, you know, the full-fledged optimization report where everything is basically added.
I've tried this before, but it's not pretty well. And documentation explains what, like on the previous slide, you had a whole bunch of optimization phases where these are explained. When you see that list of optimization phases, you don't really know which one applies to.
Well, you need a good share of compiler technology background to understand what that all means, right? So, yeah, that's the downside of it.
That's the barrier. Do we have a document saying which phases are done when?
No. And this, for example, this is something that comes out from the vectorizer. So usually our vectorizer does the following. It unrolls the loop a couple of times, sorts everything so that corresponding instructions are close together, and then jumps them together into an AVX instruction, for example. Okay, then we have the vectorization report. I will cover that after lunch. What we also have is called GAP. That's guided auto parallelization, but it's also for vectorization. And what this is, it's kind of making the compiler an interactive tool to respond back to the programmer what the compiler thinks the actual problem is in the code. So what you get is when you turn it on, for example, for this code pass, it will tell you that it didn't vectorize because it assumes that there's a data dependency by aliasing, right? And so what it tells you is, add some option to the compiler for better type-based disambiguation analysis by the compiler if appropriate, right? So the tool detects a problem, and it gives you a recommendation how to fix it, right? It cannot fix it for you because it doesn't know if this fix is actually correct or not, but it will tell you that if you add that command line option, it would be able to parallelize or vectorize that piece of code. And now it's up to you to decide if this option is actually appropriate or not. Okay, and this detects a whole load of problems, and I will show you a couple of more after lunch. Okay, profiling. So what is going on in your code? We have a tool called Loop Profiler. It's basically it's two tools, one in the compiler and one additional tool. So you tell the compiler to either profile functions or profile loops. And what the compiler does is, like in the profile guided optimization, it will create a special version of your binary code that actually records what functions are called and how many loops are executed and how often those loops are executed. And then, after running this code, you can have a look at the profile either through a Java GUI or as a text file. And then you can tell the compiler more about your loops, right? So what you basically get out of here is how much time you spent in a particular piece of code, how much that is in terms of a fraction of total runtime, the number of invocations of that particular function, how many times you exited that function. That should, closely match, hopefully, and where this actually is. Right? And this is kind of a very, very easy way of performance analysis to see what is actually going on in the code. It's like gprof, if you know the GCC tool chain, right? And we also have it in a Java GUI, where you can, more easily dig through this data. And you can filter, like only interested in the hotspots and avoid all the tail in the profile and that kind of stuff. And this is especially useful when you want to tell the compiler how long loops are running in the code. Because again, the compiler has a heuristic. It will look at the loop and say, well, if I don't know how long the loop runs, it will run 70 times. Which is perfectly legal from a compiler standpoint, would probably also trigger optimizations that are beneficial for 95% of the loops. But if your loop is not part of this 95%, you're disappointed by our performance, right? And then we have pragmas, where you can actually tell the compiler, hey, this particular loop will run a minimum of 1,000 iterations. Typically, the maximum iteration count will be 2 million, and the average count, which you can find somewhere here, down here, is 500,000. And then the compiler exactly knows what is the contribution of this loop in terms of runtime, right? And will trigger different optimizations if possible. Okay, floating point precision. This is another big topic because you can gain a lot of performance, and 20% is a lot of performance in HPC. So the compiler needs to make certain assumptions what it can do to floating point operations. And usually, the compiler cannot do anything about it. They are not, oh shit. Chris, floating point operations are not associative and commutative. Are they? No matter. They are not fully, not real numbers. That's what I'm trying to say. So you can specify what the compiler should assume in terms of precision or accuracy when executing floating point operations on the machine.